Hello everyone, in this video I'll talk about how to use those basic LCD screens and the library I've written for them, which you can use both on your projects and to help you develop your code in general. I'll first talk about how these LCDs work and how to connect them, then I'll tell you how to use the library functions. I won't go into how I wrote the library since that would take a whole video or two to explain, which I might make in the future, but for now I'll just show you how to use the functions I've provided. I'm including this video in the series since I plan on using LCDs in my future videos to display some of the parameters and etc. So, let's get started. Before we start, after I'm done with this video, I'll be keeping this LCD connected to my breadboard as you see now. You don't have to buy one for yourself, but I absolutely recommend getting one for a beginner. You can use it as a graphical interface for your projects, but more importantly than that, it'll allow you to display any variable in real time, which will help you understand and debug your codes easily. For those who don't know what debugging is or how to do it, I'll put a link down below for a separate series that I have on the topic, which I made into a separate series because it needs a lot of videos to explain and is a more specialized topic. I'll only use debugging over showing things on LCD if I have to, so you don't have to watch them, but I do recommend it. It is a must-have skill. Let's talk about LCDs first. What is an LCD? LCD stands for Liquid Crystal Display, and it's a type of display technology. How the technology works is not important for this video, and if you're interested, you can YouTube the term. But in the Arduino verse, if you say LCD, the first thing that will come to people's mind will be one of these displays. They come with different shapes and sizes, but the ones we're gonna use, which are the most popular ones, are the 2x16 and 4x20 LCDs. I haven't tested the library for all LCD sizes, but it works with these ones at the very least. The library is written for LCDs that use HD44780U chip from Hitachi, or its clones, as the driver. These LCDs will have built-in ROM that contains the characters to be displayed. So these LCDs display characters instead of us controlling each pixel. So one of those 128x64 LCDs wouldn't work with this library, since those are individual pixel controlled. Some of the sellers won't tell you the driver chip, and you can't really see it from the construction of the LCD either, since they use black epoxy to cover the chip. But all 2x16 and 4x20 LCDs I have on hand work without a problem, so as long as you buy one of those, or similar, it should be fine. Also, you'll see many LCDs that come with an I2C interface. The LCD is still the same, only it's connected to an I2C to parallel converter. Unfortunately, the library is only built to directly connect to the LCDs. Maybe I'll add the functionality to use I2C in the future, but for now you won't be able to use those. Some of these LCDs will have a backlight, and some won't, which also affects their price, so keep that in mind when buying one. The ones without the backlight will be hard to read without ambient light, and the ones with the backlight will consume more power because of that light. They also usually come with green and blue colors. It doesn't make a difference on its functionality, so it comes down to taste. Also, they usually come without their headers soldered, which means you'll also need a solder and a soldering iron as well. In this video, I'll be using a blue 4x20 LCD since I like the blue color and the bigger size gives more space to fit everything on screen. These LCDs have 16 pins in total with these labels. 2 pins for powering the LCD and the driver chip, 1 pin for adjusting contrast, 3 pins for mode select and clock, 8 pins for data, and 2 pins for the backlight, which you may or may not use depending on if your LCD has backlight or not. The chip works with 5 volts, so connect the VSS to ground and VDD to 5 volts. V0 is used to adjust the contrast, which when increased or decreased looks something like this. The contrast is adjusted by changing the voltage on the V0 pin, which can be done using a voltage divider. But in most connections online, you'll see that a potentiometer is used instead. This is because the required contrast changes a lot between different supply voltages and your setup in general, so it's better to find the perfect contrast for your setup using a potentiometer. You can leave it like that, or take out the potentiometer, measure its resistance, and replace it with normal resistors instead. A value of 10 kiloohms works well for the potentiometer, by the way. Also, in online connections you'll see that the ends of the potentiometer are connected to 5 volts and ground. I don't know if this is true for all LCDs, but all of the LCDs that I have come with a 10K resistor internally connected between the V0 and VCC. So I don't actually need to connect one of the ends of the potentiometer to 5 volts. which just increases the current consumption for no reason. So try to remove the positive connection from your potentiometer. If it doesn't change anything, then leave it off. The RS pin is used to select between data or command modes. Again, I won't talk about how I created the library in this video, so all you need to know is that we need this pin to connect to the microcontroller. The RW pin is used to select between read or write modes. With the way the library is written, you don't actually need this pin. However, you do need to connect it to ground. The E pin is the clock line, which also needs to connect to the microcontroller. Next 8 pins, starting from D0 up to D7, are your data lines, but the driver chip can operate in 2 different interface modes, which are 8-bit and 4-bit. Since this library uses 4-bit interface, the first 4 data pins can be left unconnected. But it's never a good idea to leave an input pin floating, so either connect them to one of the power lines or connect them to the E pin or the D4 pin that are adjacent. The value on these pins are ignored, so you can connect them to anything, as long as you don't leave them floating. So you only need to connect the last 4 data pins, starting from D4 up to D7 to the microcontroller. The last 2 pins are for your backlight LED. A is for anode, which connects to 5 volts, while K is for cathode, which connects to ground. In some online connections you'll see that they connect a series resistor with these pins to limit the current. I don't know if this is true for all LCDs, but all of the LCDs that I have come with a series resistor on the back side. So it's safe for me to not add this resistor, but you should make sure that yours also has this resistor, otherwise your backlight will burn and your LCD will become useless. I also recommend adding a 0.1 microfarad capacitor between the power pins for decoupling. It's fine if you don't, but adding a decoupling capacitor to every chip is always a good idea. Now, I left these microcontroller connections floating because with the way I wrote this library, you can connect these ends to any microcontroller pin that you want, given that they can be configured as digital outputs. I did it this way so you can connect them to any pin on any microcontroller you want, without being limited by the microcontroller family, or not having available adjacent pins, or not having any pins in the same port register, and etc. All you need to do is change some definitions in the header file, which I'll get to in a bit. But before I do, I'll quickly make the connections for my circuit. I'll add another breadboard to my circuit, and I'll be using this setup sideways from now on. I'll speed up my connections for you. You don't need to go through this much effort, of course. I just want it to look clean since I'll be using it in future videos as well. I also directly soldered the optional decoupling capacitor on the LCD itself to not have to connect it on the breadboard, and the lower 4 data pins together to the E pin to not leave them floating. And there we go, the circuit is complete. I've connected my pins from RA0 to RA5. You don't have to make the same connections, of course. Like I said, you can use any output pin as you like. Before I talk about the library functions, I first have to show you how to add this library to your project. In MPLAB, there's a way to make library projects. However, since this library uses 6 pins that can be individually selected, making a library project for it just doesn't work out. You can make it work, but it's just not worth it in my opinion. I won't get into why in this video, but I will eventually make a video on library projects. Instead, I'll just give you the library files, which you can directly put in your projects. I'll put a link down below for the folder named LCD, containing all of the files for you to download. The folder will contain 1 header file and 21 source files. There are multiple ways to add these files to your project, but first open up your MPLAB IDE. I'll just show you the easiest way to add this library to your project, which is by copying the files through MPLAB. I already created an empty project here, which already contains the config.h and main.c files I've been using in the series. Unfortunately, you can't just move files into your projects tab, as this is not how the files are actually stored on your PC. I've talked about all of this in the first video in the series. To add an existing file to your project, you need to right-click the project and choose Add Existing Item. Here, you can choose a file from within your project, or anywhere on your PC really. But remember, header files should go to header files directory, and source files should go to source files directory in your project. So to add the header file, you can right-click the header files directory and press Add Existing Item. Here, you can navigate to where you downloaded your library folder, which for me is my desktop. Click it, go to Header Files, and choose the lcd.h file. On the right, click Relative Path and select the copy option. This will copy the file into your projects as folder, as if you've created it. Click select, and as you can see, the file is in our project now. And if we check our projects as folder, you can see the copied file. By copying the files like this, you can move this project file wherever you want, and the library will still work, even if you delete the library folder you've originally downloaded. So the project won't have any dependencies to any external files. Now we gotta do the same for the source files, but adding 21 files directly into your project will make it impossible to see your own files. So I recommend right-clicking the source files directory and pressing New Logical Folder. This will create a subdirectory which you can rename by pressing F2. I'll name it LCD for context. Now we can add the files to this directory, which will keep things organized. Again, right-click the folder and press Add Existing Item. Navigate to the library folder, go to Source Files, and select all of the files by clicking Ctrl and A. On the right, click Relative Path and select the Copy option, and click Select. As you can see, all source files are added to the LCD subdirectory, which we can expand and collapse to keep things organized. And that should be it for the library files. Now, to use the library functions, simply go to your main file and include lcd.h. To test if you did everything right, click the Clean and Build button, and you shouldn't get any errors related to LCD. You'll get these warnings saying that a function is never called. They're just warnings, not errors. MPLAB is just informing you that there are functions in your project which are never used. And don't worry, unused functions won't take up memory. These warnings will disappear when you use their functions in your project, and if you don't want to see them every time, you can use this pragma on your project, which will suppress all the function never called warnings. Before you can use the library, you need to configure some things in the header file, so open the lcd.h file in your project. From here, you need to change the project definitions part according to your connections. Here, you need to put the tris bits of the pins you connected your LCD to, and here, you need to put the lat bits of the pins you connected your LCD to. So, for example, my RS pin of the LCD is connected to RA0 pin of my microcontroller, so here I put tris A0, and here I put lat A0. Or for example, my D5 pin of the LCD is connected to RA3 pin of my microcontroller, so here I put tris A3, and here I put lat A3. And like I said before, the pins don't have to be connected to RA pins, or any pin in a particular order. You can literally connect them to any pin individually, as long as they can be configured as outputs. You also need to define your system frequency here. Unfortunately, defining this in other parts of your project is not enough. You also need to define it here, since the library functions need it. And that's it, you don't need any peripherals. The library should just work if you did everything right. To test if you did everything right, go to your main file and write the function lcd init without passing any arguments to it. Then write the function lcd_write_string and pass a string to it, like hello world, making sure that it's inside double quotes, and program. And you should see the text written at the beginning of your LCD. Now, before I talk about the library functions, you need to know a couple of things. All of the functions start with capital LCD and an underscore to keep them organized. To see all of the functions, type LCD_ and press Ctrl and spacebar, which will bring up the autocomplete menu. I've talked about this in my useful shortcuts video in the series. Don't use or change any definitions or variables that show up in this menu. You're only supposed to use the functions at the bottom, which are denoted by this symbol. You can see the documentations for the functions here when you select them, and the type of arguments you're supposed to pass to them is also shown here. Every function is documented, so you don't have to look at this video every time you want to remember how they work. There are 3 functions which are only meant to be used internally by the library. I won't talk about those functions, so forget about them. You can double-click or press enter on a function to automatically write it. And even after writing the function, you can still check its documentation by clicking on the function and pressing Ctrl and spacebar. Also, before we start with the functions, the 2x16 and 4x20 I've talked about refer to rows and columns that the characters can be displayed at. So, a 4x20 LCD can display 4 rows and 20 columns of characters in total. For this library, the first location will not be 00, instead it will be 11, which is different than the Arduino LCD library you may have used, so keep that in mind. I'll also talk about the cursor. Cursor refers to the currently selected location in this array, which is where the next writing operation will occur. So if you have this location selected and write the character A, it will be written here. And by default, whenever a character is written, the cursor will be automatically incremented or moved to the right. There are ways to tweak these and set the cursor location manually, which I'll talk about in a bit. Now, let's talk about each function available to you. First function is LCD init. This function initializes the LCD, so you need to put it in your code no matter what. And be careful, it needs to come before any other LCD function. It takes no arguments, so just write it as is. The LCD is initialized as display on, cursor display off, cursor blink off, and cursor increment on right with no shift. We'll get to what all these mean and how you can configure them, so don't worry for now. Also, when initialized, the cursor will point to 1, 1. Second function is LCD cursor set. This function is used to change the cursor location. It takes two arguments, the first being the row and the second being the column. You can use this function to change where your characters will be written to, and the first top left location will be 1, 1. So for this 4x20 LCD, top right would be 120, bottom left would be 4, 1, and bottom right would be 420. Also, be careful, when you shift the screen, which we'll see in a bit, the cursor location will also shift. So when the display is shifted to the right by 1, the cursor location 1, 1 will point to here instead. As an example, I'll write the hello world at the location 2, 5. And you can see that the hello world starts at row 2 and column 5 like we intended. Third function is LCD write char. This function is used to write a single character on the screen, and it takes one argument, which is the character you want to write. You write characters in C by using single quotes. Mind you that, for example, this 0 and this 0 are completely different. This is just the number 0, while this is the character 0, which corresponds to the number 48 in ASCII code. I won't go into how these characters work. I've said many of times, you shouldn't watch these videos before learning how to code in C. As an example, I'll go ahead and write hello world again, but this time using single characters. Fourth function is LCD write string. This function is used to write a string on the screen. It takes one argument, which is the string you want to write. Strings in C are a bit more complicated than other languages, so I'll put a link down below for a good explanation if you don't know about them. You write strings in C by using double quotes, which automatically adds the null termination. The function itself doesn't check the string for null termination to keep the code efficient, and if the string you pass to this function is not properly null terminated, it will fail, or possibly be stuck in an infinite loop. You can directly write the strings like this, which still defines an array to store this variable behind the scenes. But if you want to display a string variable, you can define it as an array of char like this. Be careful, there is no string variable in C. Please see the links I've mentioned if you don't understand the concept. Again, using double quotes automatically adds the null termination. So if you were to define each character discretely, you would need to add the null termination manually, like this. To write this char array, you can just pass the array's name directly to the function. This array has null termination, but if you try to write a string that you read from a sensor or something, you would need to make sure that it's null terminated. As an example, I'll write hello world in all three ways you see on screen at the same time, on different lines. Fifth function is LCD write variable. This function is used to write a variable on the screen. It takes two arguments. The first argument is the variable to write, which needs to be a 32-bit integer. You can't write float variables with this function. The second argument is the left offset. It offsets the least significant digit of the variable from the left by a given amount if it's bigger than the total digit count, which allows for writing from right to left while keeping the least significant digit stationary. If you don't want any offset and just want to write the variable directly, pass 0 to it. You'll understand how the offset works from the example. Also, negative numbers are displayed as positive. This is to avoid the problem of where to put the minus symbol, or if you want a plus symbol for positive values or not. If you have a negative number, you can check if it's negative with an if statement and put the minus symbol manually. As an example, let's make a variable count up slowly and display it on screen. I'll make the offset 0 for now to disable it. I'll put a small delay as well so we can see the variable counting up. As you can see, the number is written without a problem, but the number is expanding to the right. There are many cases where you'd want the number's least significant digit, or the rightmost digit, to be stationary, while the rest of the digits are growing to the left, especially when making a user interface. This is where the offset variable comes in. This value offsets the least significant digit of the variable to be written. Let me give it an offset of 3 instead and program again. As you can see, the least significant digit is written with a 3-column offset, and the digits are growing to the left. But be careful, if the total digit count of the number ends up the same or bigger than the offset, the digits will start to grow towards the right again. Also, even if you give an offset, after the function is complete, the cursor will point to the next column after the variable. Sixth function is LCD write float. This function is used to write a float variable on the screen. It takes 3 arguments. The first argument is the variable to write, which needs to be of float type. The second argument is the left offset. It offsets the least significant digit of the variable from the left by a given amount, if it's bigger than the total digit count, which allows for writing from right to left while keeping the least significant digit stationary. If you don't want any offset and just want to write the variable directly, pass 0 to it. But be careful, the total digit count includes the integer part, the fractional part, and the dot that will be put on screen. You'll understand how the offset works from the example. The third argument is the fractional digit count. Pass how many digits after the dot to be displayed to this argument. So if you pass 2, only 2 digits after the dot will be displayed. I won't go into how float variables are represented in binary, but if you try to display more digits than what can be represented with floats, the variable will overflow. Also, negative numbers are displayed as positive. This is to avoid the problem of where to put the minus symbol, or if you want a plus symbol for positive values or not. If you have a negative number, you can check if it's negative with an if statement and put the minus symbol manually. As an example, I'll write the number 97.52 without any offset and with 1, 2, and 3 fractional digits. As you can see, numbers are written without a problem, and they have 1, 2, and 3 fractional digits like we wanted. The reason why you see 1 here instead of 2, or 19 here instead of 20, is the way in which the float variables are stored. If you want to know more about this problem, you can Google float point rounding error. I'll make another example to explain the offset argument. I'll make this variable count up slowly and display it on screen. I'll put a small delay as well so we can see the variable counting up. As you can see, the number is written without a problem, but the number is expanding to the right. There are many cases where you'd want the number's least significant digit or the rightmost digit to be stationary, while the rest of the digits are growing to the left, especially when making a user interface. This is where the offset variable comes in. This value offsets the least significant digit of the variable to be written. Let me give it an offset of 6 instead and program again. As you can see, the least significant digit is written with a 6-column offset, and the digits are growing to the left. But be careful, if the total digit count of the number ends up the same or bigger than the offset, the digits will start to grow towards the right again. Also, even if you give an offset, after the function is complete, the cursor will point to the next column after the variable. Seventh function is LCD clear. This function is used to clean the whole screen from characters. It takes no arguments, and at the end of the function, the cursor will be pointing to 1, 1. As an example, I'll write hello world on the screen and clear it after 2 seconds. Eighth function is LCD cursor increment. This function is used to increment the cursor by a column, and it takes no arguments. As an example, I'll write hello world after incrementing the cursor twice. And as you can see, the text is written 2 columns after. Ninth function is LCD cursor decrement. This function is used to decrement the cursor by a column, and it takes no arguments. As an example, I'll write hello world, then decrement the cursor once. Then I'll write a question mark instead, which should replace the exclamation mark here at the end. And as you can see, the exclamation mark is replaced by the question mark. 10th function is LCD shift right. This function is used to shift the whole screen to the right by 1, and it takes no arguments. But be careful, when the screen is shifted, the cursor locations also shift. So for example, without any shifts, the location 25 would point to here, but if you shift the screen to the right by 1, 25 would point to here instead. Also, for a 4x20 LCD, the third line is the continuation of line 1, and the fourth line is the continuation of line 2, so characters that are shifted off screen will instead pop up on a different line. This behavior is caused by the controller chip itself, so there's nothing you can do about it. For screens that are smaller than 4x20, the characters off screen will disappear for the first couple of shifts, but will also pop up on a different line if shifted further. As an example, I'll write the string hello world and shift it to the right every second. Eleventh function is LCD shift left. This function is used to shift the whole screen to the left by 1, and it takes no arguments. But be careful, when the screen is shifted, the cursor locations also shift. So for example, without any shifts, the location 25 would point to here, but if you shift the screen to the left by 1, 25 would point to here instead. Also, for a 4x20 LCD, the third line is the continuation of line 1, and the fourth line is the continuation of line 2, so characters that are shifted off screen will instead pop up on a different line. This behavior is caused by the controller chip itself, so there's nothing you can do about it. For screens that are smaller than 4x20, the characters off screen will disappear for the first couple of shifts, but will also pop up on a different line if shifted further. As an example, I'll write the string hello world to the right side and shift it to the left every second. Twelfth function is LCD shift reset. This function is used to reset all shifts currently applied to the LCD. It takes no arguments, and at the end of the function, the cursor will be pointing to 1, 1. As an example, I'll write hello world, shift it to the right by 3, and reset it back after 2 seconds. Thirteenth function is LCD configure LCD display. By default, your write operations will be displayed on screen automatically, but you can change that. Using this function, you can make it so the LCD doesn't show the characters written on screen. The characters will still be there, and you can still write to the LCD like normal. They just will or won't be displayed. This function takes one argument. If you want the characters to be displayed on screen, pass 1 to it, and if you want the characters to not be displayed on screen, pass 0 to it. By the way, this won't enable or disable the backlight, since it's not connected to the chip at all. The backlight LED is independent of the controller chip, and is only controllable through its power pins. As an example, I'll write hello world and enable and disable the display on repeat with 1 second delay. As you can see, the character display is toggled each second. Fourteenth function is LCD configure cursor display. By default, the cursor line is not displayed, but you can change that. Using this function, you can enable the cursor line that is displayed under the characters on the cursor's current location. The cursor line can also be enabled at the same time as the cursor blink. This function takes one argument. If you want the cursor line to be displayed, pass 1 to it, and if you want the cursor line to not be displayed, pass 0 to it. As an example, I'll enable the cursor and increment its location on repeat with 1 second delay. As you can see, the cursor line is displayed and it points to the cursor's current location. 15th function is LCD configure cursor blink. By default, the cursor's location won't blink, but you can change that. Using this function, you can enable the blinking that happens on the character on the cursor's current location. The cursor blink can also be enabled at the same time as the cursor line. This function takes one argument. If you want the blinking on, pass 1 to it, and if you want the blinking off, pass 0 to it. As an example, I'll enable the blinking and increment the cursor's location on repeat with a 1 second delay. As you can see, the character is blinking on the cursor's current location. 16th function is LCD Configure Entry ID. The ID here doesn't stand for identification, it stands for increment decrement. By default, on each write operation, the cursor is automatically incremented. But you can change that by using this function. You can't configure it to not move, but you can make it decrement instead if you want. This function takes one argument. If you want the cursor to increment on each write, pass 1 to it. And if you want the cursor to decrement on each write, pass 0 to it. As an example, I'll configure it as increment and write hello world on the first row. Then I'll configure it as decrement, put the cursor to 212, and write hello world again on the second row. As you can see, the first hello world is written as normal, while the second hello world is written backwards, since the cursor is decrementing on each write. 17th function is LCD Configure Entry Shift. By default, the screen doesn't shift when a write operation occurs, but you can change that. You can make it so the screen shifts whenever a write operation is performed. This function takes one argument. If you want the screen to shift on each write, pass 1 to it. If you don't want the screen to shift on each write, pass 0 to it. When the shifting is enabled, if the LCD is configured to increment its cursor on each write, the screen will shift left. While if the LCD is configured to decrement its cursor on each write, the screen will shift right. Since the shifting occurs towards the opposite side of the cursor's movement, the text will seem as if it's coming out of the cursor, while the cursor stands still. You'll understand it better with the examples. Most people won't enable this shifting, since shifting the screen also shifts the cursor locations. For example, without any shifts, the location 25 would point to here, but if you shift the screen to the right by 1, 25 would point to here instead. So, unless you actively keep track of your shifting, cursor locations will become almost random, and you won't be able to write to a specific location. As an example, I'll first configure the LCD to increment the cursor on write, and enable the shifting on write. Then, I'll enable the cursor blinking, so we can keep track of where the cursor is. I'll put the cursor to 114 and write hello, but I'll write it using chars while putting 1 second delay between each write, so we can see step by step how the write operation occurs. As you can see, since the shifting occurs towards the opposite side of the cursor's movement, the cursor seems like it's standing still, while the text comes out of it. Now, let's do the same example, but for the LCD configured to decrement the cursor on write. I'll change the code so the cursor decrements on write, and the cursor is set to 17 instead. And of course, the shifting on write is still enabled. As you can see, the cursor again seems like it's standing still, while the text comes out of it. 18th function is LCD Add Character. You can use this function to make and add your custom characters to be displayed on screen. It takes 2 arguments. The first argument is the char array of your character. The second argument is the location to add this custom character into. Be careful, you can only add 8 characters in total, limited by the controller chip itself. So you only have 8 locations to add characters into. These locations are from 0 to 7, so make sure to not pass any other number to this argument. To generate a character, open up your browser and search for LCD Custom Character Generator. Click the first link and it should bring you to this page. This page is mainly meant for Arduino, but you can also use it for this library by tweaking the code a bit. As an example, I'll just make a smiley face character here. And you can see the code changing here as I generate my character. After making your character, you need to copy this part of the code. We don't care about the rest. Paste the code in your project. This will cause errors since there's no byte variable in X8 compiler, so replace the byte with char. You'll still get errors since you can't represent binary in X8 like this. You need to put another 0 before the B. Also, this variable name can be anything you want. And that's it. You can use this variable to add your custom character. To add your custom character, pass the name of this variable to the add character function. then specify the location to put this character into. I'll put it in location 3 for this example. Now, to use this character, use the write_char function. Inside of it, pass the location of where you added your custom character into. So for this example, it's 3. Let's program and see. As you can see, the custom character is added to the LCD and displayed on screen successfully. And we're done. That's it for all functions. As a side note, I may update the library in the future if the need arises, so some things may be different for future viewers, but if such a thing happens, I'll put a readme text in the download file containing the changes. If you go back to each function's example and pause while building, you can see that depending on the function used, you may need thousands of bytes of programming memory, which you may not have for older, cheaper or smaller microcontrollers. Functions like write_float can take over 5,000 bytes of programming memory alone, and obviously you only need that programming memory once. After the first function call, you won't need 5,000 bytes again for the subsequent calls. Float point operations are very heavy for microcontrollers that don't have a specific hardware for it, especially for 8-bit ones. But most other functions aren't this heavy. Just make sure you have enough programming space for your project before buying a microcontroller. Also, depending on the function, you may need up to 4 hardware stack levels. I've said this before, hardware stack stores the return locations of your function calls and is limited in hardware for 8-bit PIC microcontrollers. So you are limited in how many functions you can call inside of another function without returning. For newer chips, this shouldn't be a problem. For example, this chip has 31 level hardware stack. But if you have one of those old chips that has 8 level hardware stack in total, this may cause a hardware stack overflow condition if the LCD functions are called inside of a bunch of your functions, which will completely bug your code, so be careful. And that's the end of the video, and thank you for watching. If you liked the video, you can always leave a like and subscribe. It's always appreciated, and I'll see you in the next video.